Okay, so today we are going to discuss about one kind of bifurcation known as saddle node bifurcation. So before we begin to know what is saddle node bifurcation, we'll see an example. Okay, so the example is x dot is equal to r plus x square. Okay, r is some parameter. Fine. So now let's see what if r is greater than 0. Okay, if r is greater than 0, then what are its fixed points? Okay, if r is greater than 0, this term is positive. X square is always going to be positive, so the sum of positive and positive will be positive, right? So I cannot equate this one to 0. Therefore, when r is positive, then no fixed points. Okay, no fixed points. Okay, what if r is negative? Okay, what if r is negative? If r is negative and then this is a negative value and this is a positive value, and therefore I could write x star, which is to represent the fixed point. X star square is equal to minus r, where x star is equal to plus or minus root minus r. Okay, so which is a real number. So we will have two solutions. Okay, what if r is equal to 0? What if r is equal to 0? Then I will have x star square, which is equal to 0, and that will give me only one solution, which is x star is equal to 0. Okay, now if you see here two fixed points and here only one fixed point. Okay, now let's plot this one. Okay, so when r is negative, then x dot is equal to r plus x square. Give me this curve. Okay, where r is minus 1. At that time I am getting two solutions. One is minus 1 and another solution is x is equal to 1. Okay, so from this when r is negative, we have two solutions, minus r, where for this case r is equal to minus 1, so minus into minus plus, so root 1 is just 1, so plus or minus 1 is the solution, and we are getting that solution. Yes. Okay, and now, and for our case, this r is going to be our control parameter, and I am going to slowly tune the control parameter. I am going to increase the control parameter. Okay, so if I slowly increase the control parameter, look what's happening. What's happening to this parameter? What's happening to the fixed point? The fixed points are changing, but still the system is having two fixed points. Only the position of the fixed points are changing, right? But the character that it's having two fixed points, where by the way, this is a stable fixed point, and this is an unstable fixed point. Okay, so the character that it has one stable fixed point and one unstable fixed point, that part is not changed, that remains unchanged. Okay, now I'm further increasing the r value, and when r reaches 0, see these two fixed points, right, these two fixed points collide each other, okay, and formed into a single fixed point. Okay, so now tell me what kind of fixed point this is. Is it stable or unstable? Actually, it's neither. Okay, actually, if we see this side, x dot is positive, so the x will move towards the fixed point, but here the x will move away from the fixed point. Okay, so it's half stable. Okay, and now what will happen if I keep on increasing this r value? If I further increase this r value, there is no intersection with this x-axis. Okay, and therefore there is no fixed point. So suddenly the fixed point got disappeared when r has been tuned to 0. Okay, and 0 and above. And this behavior, this sort of behavior where two fixed points, where one is stable fixed point and another one is unstable fixed point, they come together, they collide, and then they disappear. This fixed point is, this character, this bifurcation character is known as saddle node bifurcation. Okay, so that's an example of saddle node bifurcation. Now based on this example, we'll discuss about something called bifurcation diagram. Okay, so let's see what is this bifurcation diagram. So the bifurcation diagram is nothing but a plot of r versus x. R versus x star, the fixed points. Okay, so once again I will write the system dynamics, which is x dot is equal to r plus x square. Okay, and the relation between r and x star, where x star is the fixed point, is r plus x star square equal to 0, right? So x dot, when x is equal to x star, then x dot is 0. So from that we have got this relation. And now let's plot this equation. Okay, if I plot this equation, what do I get? Let's see. If I plot this relation, what do I get is this curve. Okay, so this is the curve I will get, where this axis is the r. Okay, this axis represents x star. Okay, now when r is some negative value, let's say -1, then we have two solutions. Okay, so we have two solutions. One x star is -1, one x star is 1 and another x star is -1. And if I keep on increasing, and we have still we have two solutions. Okay, but when r is equal to 0, then suddenly this solution and this solution collide into a single solution, and upon further increase in r, there is no solution. Okay, because there is no intersection of this curve with that vertical line. Okay, and this is known as bifurcation diagram. But in this bifurcation diagram, one information is not clear, which is, as we mentioned, that there are two fixed points, where one fixed point is a stable fixed point and another fixed point is an unstable fixed point, right? So here, which is stable and which is unstable? For that, let's plot this one once again. When r is negative, only then we are having two fixed points. Okay, and this is a stable fixed point, this is an unstable fixed point. So the stable fixed point has a value of x star in the negative side, and unstable fixed point is having a value in the positive side. So therefore, from that I could say that this branch of the curve, which represents the negative x star, is a stable fixed point curve, where this one is the unstable fixed point curve. So in order to distinguish this stable branch and unstable branch, the way we represent, the way in this book which has been represented is in a dashed line to represent the unstable fixed point and a solid line to represent the stable fixed point. Okay, so that's how we represent, that's how we make the bifurcation diagram and get the information. If a bifurcation diagram is given, then from this bifurcation diagram we could understand when the bifurcation will occur and what will be the fixed points, and if the fixed point occurs, then will that be a stable fixed point or unstable fixed point? All those informations can be obtained from the bifurcation diagram. Okay, fine. Now let's see one example. So the example we are going to discuss is, okay, the example we are going to discuss is the following. X dot is equal to r minus x minus e to the power of minus x. Okay, so this is the system, and this r is going to be the control parameter. And now by changing the control parameter, is there any bifurcation? In particular, is there any saddle node bifurcation? That's what we are going to discuss. Okay, one sec. Okay, so let's unplot all those things, and if we see the equation once again, this is the equation, and what we have to do, we have to draw the bifurcation diagram. And the bifurcation diagram, how do we draw the bifurcation diagram? We draw a curve by making this x dot equal to 0, so that at that time x becomes x star. So r, which is equal to x star plus e to the power of minus x star, right? So this is the curve which I have to plot. So let's plot this one. Okay, so where here y represents x and the x represents r. If I plot, then this is the curve I am getting. Okay, if you see, this curve is very similar to this one, where this is my r and this is my x star, and if I keep on increasing my r value, and suddenly at this point the bifurcation occur, where we are getting two fixed points. In this two fixed point, one is going to be a stable fixed point and another one is going to be unstable fixed point. Okay, but instead of plotting this, I'm going to plot something different. Okay, so what is the thing I'm going to plot? So in this equation, okay, in this equation I'm going to consider so this is basically f of x, right? So what I'm going to consider is at equilibrium, sorry, not this, at equilibrium or at x dot is equal to 0, okay, I'm going to write g1 of x star is equal to g2 of x star. What is this g1 and g2? So g1 and g2 are nothing but so g1 is r minus x or r minus x star, okay, and g2 is this term, okay, e to the power of minus x star. Okay, so at equilibrium this part and this part, okay, these two functions are going to be same. Okay, so at equilibrium these two points are going to be these two functions are going to be same. Okay, so what I'm going to do is I'm going to plot these two things separately. Okay, so what I'm going to do is I'm going to plot g1 or x versus g1 and x versus g2. Okay, and when these two things are intersecting, okay, when these two things are intersecting, then at that time I am getting the fixed points. Okay, let's plot these two functions. So let's plot these two functions. So one is this one, which is g1, and this is g2. Okay, and when r is equal to 0, they are not intersecting. Okay, and now I am going to slowly increase the r value, and if I increase the r value, see this g1 is shifting, g1 line is shifting, and when r is equal to 1, okay, when r is equal to 1, there is an intersection. Okay, and if I keep on increasing, then I am getting two intersections, right? If I further increase, you could see it clearly. So one intersection at this point and another intersection at this point. Okay, I'm getting two intersections. Okay, initially when r is less than 1, no intersection, and r is more than 1, intersection. So the bifurcation occur when r is equal to 1. Okay, so that's one of the important point I need to know, okay, in order to characterize the system. Fine. So we identified the bifurcation occur at this point, but how can I say just by having this equation? The way I could say is, if you observe this picture once again, when r is equal to 1, okay, so it is intersecting at a single point, and at that point if you see, this curve as well as this curve is having a common tangent, right? it's having a common tangent. So that's one more condition in order to identify this bifurcation point, to calculate that bifurcation point analytically. Okay, so the tangent of this curve and this curve has to be same. Okay, so it means the condition is g1 of x, and the tangent is, I am differentiating, so prime, okay, which should be equal to g2 prime of x. Okay, so what is g1 prime of x? What is g1? So this one, r minus x. So if I differentiate with respect to x, what do I get? I'll get minus 1. Okay, and if I differentiate with respect to x, what do I get? I will get which is equal to minus e to the power of minus x. Okay, so which means I can remove this minus and minus. Now from this equation what I can say is this occur when x is equal to 1. Okay, sorry, this occur when x is equal to z, oops, x is equal to 0. Okay, so now what I'm going to do is I am going to put that x is equal to 0 value in this equation. Okay, or in this equation, what do I get for r? R minus 0 is equal to e to the power of minus 0. So this side I will get just r, which is equal to e to the power of 0, which is just 1. So the bifurcation occur, let's call that the critical r value. So the bifurcation occur when r is equal to 1. So that's what we have got, right? So the bifurcation occur when r is equal to 1, right? Which is a saddle node bifurcation. Okay, so if I increase the r further, we have got 2 fixed points, right? So as an exercise, I want you to identify among these 2 fixed points, I want you to identify which fixed point is stable and which fixed point is unstable. Otherwise, in this bifurcation diagram, okay, so there are 2 branches. You need to identify which is a stable branch and which is an unstable branch. Okay, we'll see some other bifurcations in the next video. Thank you.